It is.
Yeah, but there's no hurry.
Start today. As you all probably have heard, we have an e-learning day on Monday. So what that will consist of is sometime over the weekend, probably I will post Monday's lecture. So you can watch it on YouTube or whatever. Yeah, so that'll be posted over the weekend. Monday, I guess nobody's going to be here. If you need me, you can email me. I will be working at home. I can even get on Zoom by appointment if you need to talk to me really quick. I'll probably have my usual meetings, I'll probably just be working at home. So, but I'm not going to turn on my Zoom meeting for like 4 hours and sit in my living room. So, okay, let me say a couple of words about the next homework set. The first one, this is kind of a connection with maybe some of the stuff that you might have seen in linear algebra. You might have seen these like orthogonal matrices. This, the set of matrices like this show that this is a subgroup of the 2x2 invertible matrices over R. Use the subgroup criteria, it'll make things not so bad. Show the operation given by given a matrix here and a vector in R2, my operation here is just multiply the matrix. That should barf out another vector. Show that this is an action of G on R2. And I'm going to tell you what an action is today. And then explain geometrically how this action works. So this group action gives you something that's kind of geometric here. Number two, this is a problem that I promised you. We came up with this. This result was part of one of our theorems, I believe. Show that if you have a homomorphism from G to H, and X is an element of G, show that if the order of X is N, and X to the K is 1, then N divides K. That first one doesn't have anything to do with the homomorphism. And number two, show if the order of X is N, then whatever X goes to over here, the phi of X, it has to have an order that divides N. So in particular, if the order of X is finite, then it has to go to an element of finite order. Number three, this is kind of a fun one. I'm going to give you a hint on number three. A problem from your previous problem set will make this pretty easy. You'll probably have to do a computation, but there's a theorem that you proved in the last problem set that will make part of this easy. Consider the subgroup of S9 generated by the permutations 173526 and 28153649. Find the order of the subgroup and find a familiar group which XY is isomorphic. That last statement is what you will be helpful with from the last homework. Number four, let G be a group. We talked about automorphisms last time. They're homomorphisms from a group to itself that are both one-to-one and onto. We define aught G, the automorphisms of G, to be all the automorphisms from G to G. There you go. Show that aught G is a group under function composition. So show that this collection of automorphisms is actually a group cell. Suppose we define phi sub G, phi sub little g from the group to itself by phi sub G of X is GXG inverse. This is called conjugation, when I take X and I slap it bookends with an element that's inverse. Show that this thing is an automorphism. And number C, show that the correspondence G corresponds to phi sub G as defined above is a homomorphism from G into aught G. What is its kernel? And I'll tell you what a kernel is today too. Number five, let G be a group and XY elements of G of orders M and N respectively. This is actually kind of a really cool, this last one's a kind of a cool computational theorem. And it'll be very useful. If the two elements commute, if XY is equal to YX, so if the order doesn't matter, then the order of XY must divide the least common multiple of M and N. And there, that least common multiple comes up. These properties of integers show up a lot. That's why first homework. Number two, show that if the two elements commute and the subgroup generated by X intersect the subgroup generated by Y, it's trivial, is only the identity, then the order of XY is exactly equal to the least common multiple of integers. This is a very useful thing for computing orders of elements and groups, if you happen to know that. Okay, any questions on that? Yes.
For the homework due today, like when it says we can just like cite anything about your algebra, like, that to be like, it is.
Here, let me tell you some
the
good facts from linear algebra that might be useful. The product of two upper triangular matrices is an upper triangular.
Right, so we
matrix.
can just say like, it is known that,
In fact, please do.
okay,
The determinant of a product of two matrices. And here's another biggie that'll help. The inverse, if you have an upper triangular matrix and vertical, its inverse is also up. You can quote that with impunity. Okay, other questions?
so.
Okay, so let's. Yes,
The first question.
do I say colon equals? Was it something like? You haven't had the question like this. Was it a colon equals?
Yeah.
Oh. Colon equals set of matrices, cosine theta, blah, blah, blah. That means we're defining this to be. Right? I mean, it doesn't matter. I could have just written G equals. It doesn't make a difference. But when you see the colon equals, that means G is defined to be this, right? Okay. All right, last time we were talking about subgroups, and I gave you the famous and useful subgroup criteria. If H in G is a subset of group G, and H is not empty, so I want it to be a non-empty subset, then H is a subgroup of G. If and only if for all X, Y, and H, X, Y inverses H. And we proved this last time, and hopefully I'm going to be able to apply this a little bit today. I'm going to start off by telling you what a group action is, and I'm going to use so we'll have some natural subgroups that come up from that. Definition 314. Let P be a group and a non-empty set. I'm going to define something called an action of the group G on the set A. Action of G on is a function from G cross A into A. And this is often written G acts on A, GA. So take it, it's sort of like scalar multiplication in a way. Take an element of G times element of A, and this gives you a new element that's often written GA, which is in the set A. But not just any function. I want it to behave nicely in a couple ways. Such that, number one, the identity of G acting on A is equal to A. So in this action, I want the identity to leave everything in the set alone. And two, for all X, Y and G, A and A, X acting on, Y acting on A. So take A, act on it with Y, and then act on it with X. Should be the same thing as the element XY acting on A. So something like associativity, if you will. This is what a group action is. Let me give you a couple examples here. Example one. The group acts on itself by left multiplication. So we'll suppose here X, Y is in G and A is in G. Why did I write them separately? Because I'm thinking of A as an element of the set. It doesn't matter. It's just notational. And X acting on A is just the normal XA and G. This is a group action because when I multiply anything in the group by the identity, it leaves it alone, right? So it's going to satisfy this first bit. And this right here is just the associative property of multiplication in a group. So any group acts on itself by left multiplication. Here is another action. A group can act on itself by conjugation. And I'm going to show you what I mean by conjugation. Let G be an element of G, and think of the element A and G as an element of the set. G's action on A, and this is actually an important action, is, it's enough to make you gag. This is called conjugating A. G's action on A just goes GAG inverse. Let me ask you a question real quick. What happens in the group if G and A commute? That is, if GA and AG are the same thing, what does this action do to A? Nothing. That's right. Because if G and A commute, I can flip these two, and then the GT inverse will kill each other, right? And so this would be G acting on A as A, right? So this is only interesting if the group is not abelian. If everything commutes, this is just what we call the trivial action, right? I'll bring that up in a moment. Let me prove to you that this is an action. This is the identity acting on A. This is the identity A, identity inverse, right? And I don't know much, but the inverse of the identity is the identity, and EAE should be A. So check. The identity doesn't do anything, as I hoped. Everybody okay with that? And if X and Y are in G, and A is in G, if you look at X acting on Y acting on A, well, let's see what this is. This is X acting on, my rule here is this is Y, A, Y inverse. Everybody agree with that? Now, my rule here is this should conjugate this whole mess, right? So my rule here now becomes X times Y, A, Y inverse X inverse. Okay so far? So let me do a little prestidigitation here with the parentheses. So this is, I'm gonna write this as X, Y. Anybody see another way to write this? Correct. This is X, Y inverse. Do I agree with that? And so this is actually X, Y acting on A. So this conjugation is in fact an action. And like I said, it's boring if the group is abelian. Here's another action. I probably should have put this one first, but almost always when you make a definition math, there will be a smart aleck silly example. And here's my smart aleck silly example here. T acting on A is equal to A for all G and G. This is called the trivial action. It just leaves everything alone. It's fairly easy to check. This is an action, but it's kind of boring. You don't get anything. Here's another action. This is one for your homework. This is linear algebra. This is the set of 2 by 2 invertible matrices. This acts on R2 by A operating on a 2-dimensional vector. So what do? Just take your vector, you stick it into linear transformation there. And what does this do? It outputs another vector in R2. Right? It's easy to show that this is in fact an action. Here's another action. Take the collection of all, take the collection, well, this is basically a group acting itself. When I play with the Rubik's Cube and mess it up, when I do a scramble, do another scramble, that's an action. It's the group acting on itself by left multiplication because I just compose the scrambles in a row. So group actions actually are very important because when you have a group acting on a set, it often can show certain symmetries to the set and you get certain insights to what's going on. Whatever it happens to be you're studying. So let me give you a definition here. I'm going to define let G be group. And so I've got some group and I've got some non-empty set. I am going to actually, I don't want it to be an arbitrary set. I want this to be a subset of G. There we go. That's a little better. So I want A to be a non-empty subset of G. Number one, this is called the centralizer of A and G. This is the set of everything in G such that G inverse is equal to A. Yeah, it's a set of everything that conjugates A and leaves it alone. I think in my notes I've got the G inverse here and the D here. It doesn't matter. This is also another way to think of this. I can multiply both sides of this equation on the right by G. So really what this is, if you think of it this way, is this is the set of everything in G that commutes with everything in the set A. This is called the centralizer of A in G. Number two, the center of G. I pull this one out. This is the set of G and G such that G, A, G inverse is A for all A in G. Actually, can somebody explain to me why the center of G, this is called the center of G. Can somebody explain to me why the center of G, the number two, is actually a special case of number one? How could I choose A here, capital A, so that this thing is equal to the center of G? Just make it be all of G. So this is actually another way to do it. This is the centralizer in G, not just of A, but of all G. Yes.
Saying which is the special case of which? Which one's the special case?
This one's a special case of this. If you take A, if you take your A to be capital G,
Okay.
then you recover this here.
Okay.
And finally, this is the normalizer. This is G and G, such that G in G inverse is in. Out there, didn't I? That's not an N, that's an A. Perhaps I should make clear, this is called the normalizer. N for normalizer of A. Now, let me explain to you what do I mean, I understand what this is, right? Because G times A times G inverse, that's some element of the group. I'm not too sure what this is because this is a set, right? Well, what is this? I think this is, the notation is suggestive in the following sense. G, A, G inverse. This is another set, and it's just, it's just the collection of all the four elements of the form GA, G inverse as you let A run through all the elements of A. So it's just collect all these elements as A runs through A, and that's what this is. If this set is equal to this, then we say G is in the normalizer. Or G is, yeah, G's in the normalizer of A and G. Okay. Let me, it might be instructive to actually notice that CG of A are both subgroups. Let me prove this for you. And I'm not gonna go through this in the most efficient fashion. I want to go through this to kind of get you familiar with what's going on here. I'm gonna prove this first. All right? I don't know about you guys. How many of you are struggling a little bit to wrap your head around this? All right? I know I am a little bit. So this is just a set of everything that when you conjugate the set, you get the set. So you get everything in here. It's exactly the same list here. Let's go through this. I first claim, I'm gonna be careful here. I first claim that this normalizer set, whatever I call it, is not empty. Can anybody identify something that must be in the normalizer? Good, the identity. Because E inverse is the set E inverse as A runs through A, right? That's what the normalizer, or that's what the set is, right? But if I'm a lazy man, and I am, what is an easier way for me to write E inverse? Just A. And I don't know much, but the set of all A, such that A is an A, is A. So, okay, I've got that. It's not empty. Now, let's use the subgroup criteria. Suppose X and Y are in the normalizer in G of A. Let me carefully write down what that means. X inverse is A, and Y inverse is A. Agreed? Let me also note that for all A in A, Y inverse therefore, AY inverse equals Y inverse A prime. And so now multiply by Y on both sides. A is equal to Y inverse A prime Y. So what we've shown is for every A in A, A is in Y inverse A Y. Right? So for all A in A, there is an A prime such that Y inverse A prime Y is equal to A. So everything here is contained in here. Also, I'll look at this as an exercise. Y inverse AY is contained in A. So A Y inverse AY. So what I've shown here, and this is a subtle thing, but what I've shown here is it doesn't matter if you lead with X or X inverse, right? If X is in the normalizer, then so is X inverse. Really what I've done is I've checked that inverses are in here. Let's do the subgroup criteria. if you look at this right here, this is X, Y inverse A, Y X inverse. Let me put the parentheses right here. And note that this is A. So this is X, A, X inverse. Because we proved here that this thing is A. And this is A because X is in there. So the normalizer in G of A is a subgroup of G. Let me add the brief remark here that also centralizer in G of A is a subgroup of the normalizer in G of A. One, if X is in the centralizer in G of A, then X A X inverse is A for all A and A. That's what it means to be in the centralizer. Therefore, so in other words, the centralizer in G is contained in the normalizer, right? Because every time you conjugate A, you get A back. So if you conjugate everything in A, you'll get A back. So it has to be in the normalizer. There's that. Two, the identity of G is in the centralizer in G of A. That's even easier to show than for the normalizer because if X is the identity, then it leaves it alone. So there's that. And finally, three, if X, Y is in the centralizer in G of A, then X, Y inverse times A, X, Y inverse is equal to X, Y inverse A, Y, X inverse. Because A is in the centralizer, it commutes with Y, and this is X, A, X inverse. X is also in the centralizer, so you commutes with X, and I get A. So the centralizer is in fact a subgroup of the normalizer. The subgroup criterion does make this a bit easier than having to pick through all the separate details. Any questions on this so far? Okay, let me give you any questions. Yes.
Can you walk through the number 3 again?
Okay, so X and Y are in the centralizer of G of A, right? So what I'm doing is I'm making sure that X, Y inverse is also in the centralizer because I want to use the subgroup criterion. So I conjugate A by X, Y inverse. And then, are you okay with this step? I got rid of the parentheses here and I just turned this around and inverted them, right? Now A and Y commute, right? So I can slip that Y over and cancel it out, leaving me with this. Okay? And now X and A commute, so I can slip that A out. Now I get X inverse. So does that clear up where all that business came from? Other questions? Okay. Here are two important groups that are associated with actions. And then I'm going to give you two groups that are associated with homomorphisms. Yeah, I'm going to just list them out there and then we'll talk about this a little bit. Theorem 317. Let G act on the following on set X. The following are subgroups of G. following are subgroups. Number one, let S be an S. GS, which is the set of G and G, such that GS equals S. This is called the stabilizer. This is called the stabilizer of the element S, right? So it's just everything in the group that leaves S alone. And more ambitiously, I'm going to call this K. This is the set of G and G, such that G leaves S alone for all S and S. This is called the kernel of the action. So let me kind of distinguish between these two. Maybe I will. Why this is true. Pick your favorite element out of S. It's got some element in it. Now look at everything in the group that leaves it alone under this action. This is called the stabilizer of S, and I think the terminology is suggestive. Stabilizer means it's just everything in the group that leaves that thing alone. That's a subgroup of G, and we'll see why that's true in a moment. And K is more ambitious. K is like a stabilizer on steroids, because what it is it's a set of G and G that stabilizes everything in the set, not just one little point, but it leaves everything alone. Now it occurs to me that maybe there's nothing that leaves everything alone. Or is there? Somebody tell me why there has to be at least one thing that leaves everything alone. The identity. That's one of the things about an action is the identity leaves everything alone. So if nothing else, in K, I've at least got the identity of the group, right? Let's see why these are groups or subgroups of G. This is good practice, I think. G, S, and K are not empty, as E is in both. So now all I got to do is use the subgroup criteria, right? Let me first make the following remark. If GS is equal to S, which seems to be kind of a big theme here, then G inverse GS equals G inverse S. Everybody agree with that? I just put a G inverse on both sides, right? Now, what do I know about group actions? This thing is the same thing as G inverse G operating with S. And what is G inverse G? It's the identity, right? So G inverse. So my remark's going to be useful here. So if G leaves S alone, then G inverse also leaves S alone, right? So let's get to the business of showing that GS and K are subgroups. Number one, let X, Y be in GS. So remember, I already know that GS is not empty. I've made that remark up there. This means that X acting on S is S and Y acting on S is S. So if you look at XY inverse acting on S, this is X acting on Y inverse S. But Y leaves S alone, so Y inverse leaves S alone by this remark here. Everybody agree with that? Okay, so you're left alone, so this is just X operating on old lonely S. But X acts trivially as well, so this is S. Therefore, XY inverse is in GS, so GS is a subgroup of G. And there you go. The proof that the kernel of the action is almost exactly the same. It's just now it's for all S and S, right? So the kernel is K, the kernel of the action is also a subgroup. Any questions on that? All right. Here are, okay, so keep this in mind. When I talk about group actions, they're going to come up quite a bit. These are two very important subgroups of the group acting on the set. The stabilizer of some particular point and the kernel of the action. I'm going to give you a theorem of the same sort of spirit, but instead of actions, I'm going to talk about homomorphisms. So suppose that I walk up to you on the street and I give you a homomorphism. Let phi from G to H be a homomorphism. The following are, well, I'm going to put this. A per phi, which is the set of G and G, such that phi of G is the identity of H, is a subgroup. The kernel. How many of you heard the terminology kernel in linear algebra? It depends on who you had, perhaps. Probably you all heard the term null space, right? If you go back to the linear algebra days and you look at a linear transformation, which basically, as we said last time, is a linear transformation is at its beginnings, it's a homomorphism of abelian groups because the vectors actually form an abelian group. This basically is the null space. It's all the crap that goes to zero, right? Here, EH, that represents sort of the zero vector that you would have had in linear algebra, right? So this is sort of like the null space in a certain sense. Phi, the image of phi, this is the set of phi of G. As G ranges through G, is a subgroup of H. So the kernel, everything that goes to the identity here is a subgroup of G, and the image, if you will, the image of phi is a subgroup of H. Questions on that? Okay, let's see why they're subgroups. Why the kernel is not empty. What's one thing that for sure has to go to the identity of H? The identity of G. That was one of our properties of homomorphisms last time. It has to take an identity to an identity. So for sure, I've got that going, right? So it's not empty. So now all I have to do is use the subgroup criteria. So let X and Y being the kernel of phi. Now consider phi of xy inverse. This is a homomorphism. And so this is phi of x and phi of y inverse. Right? And there's one more bit of algebraic prestidigitation I can do to that y inverse. Anybody tell me what I can do? Yeah, I can pull this out, right? So this is phi x, phi y quantity inverse. So since x is in the kernel, this is E H, and this is E H inverse, which is E H. So the kernel of phi is a subgroup of G by the subgroup criteria. Right. How about part B? I claim now that the image of phi is a subgroup of H. So let's prove this. Well, one thing I know for sure that's in the image of phi is the identity, because the identity of G goes to, so at least I've got the image, at least I've got the identity of H in the image. Everybody okay with that? So it's not empty. So celebration time, I can do the subgroup criteria. So now let H1 and H2 be an image of phi. Now, let me pause for a minute and say, nobody said that this homomorphism is onto. So if I just pick two elements of H at random, there's no guarantee they're in the image of phi. In fact, the image of phi might be just the identity. Who knows? Right? What does it mean for H1 and H2 being the image of phi?
Must be some G and G such that phi of G equals H1, H2.
Right, there's something back in G that goes to them. So that's probably going to help me out. So let me think about that. So there exists G1, G2 in G such that phi of G1 equals H1 and phi of G2 equals H2. I agree with them. That's just what it makes me in the image. And let me manipulate this one a little bit. I'm going to take the inverse of both sides. What's another way I can write this animal here? Okay, now I'm going to do just the opposite of what I did before. I'm going to put the minus back in. Right? Everybody agree with that? Notice G1 inverse is, of course, an element of G because it's a group. Yes.
I know this is a silly question, but how do we know that H2 has an inverse?
Because, we know because H is a group.
Oh, H is a group.
Yeah, it's a
Okay.
group. Yeah. So whenever I say, so I should probably clear that up. Whenever I say F from Barney to Fred is a homomorphism, I implicitly mean that Barney and Fred are both whatever the structure is, in this case, groups. Right? So everybody with me so far? Now look at H1, H2 inverse. This is phi of G1 times phi of G1 inverse. which is B G1, I'm sorry, this should be, for reasons unexplained, I wrote a 1 there when that should be a 2. G1, G2 inverse. Therefore, H1, H2 inverse is in image of phi, which is now a subgroup of H. So once again, the subgroup criteria is safe to be. Okay, any questions on that? Look at the last exercise in this section, notice 319. Of course, if you have a homomorphism, in terms of image, what does it mean for this homomorphism to be onto? What does it mean about the image of phi? It must coincide with what? H, right? Everybody agree with that? So this homomorphism is onto if and only if the image of phi is H. It's 1-to-1. You might remember this from linear algebra. This homomorphism is 1-to-1 if and only if the kernel of phi is what? Is the identity of H, right? Do you remember that about linear transformations? It's 1-to-1 if and only if the null space was only the zero, it was only the zero vector. It's the same thing here. So see if you can prove that the kernel of phi equals the identity of G if and only if phi is 1-to-1. So enjoy your e-learning day, stay safe, and we will see you by Wednesday. Yes. There's a math club this afternoon. Good. It's got factorization. Other than that, we'll see you next time.
I was so tired.